We physicists have waited 100 years since 1916 for this photograph. Welcome to Astral Voyager. Today we're diving into one of the most mysterious and fascinating phenomena in the universe, black holes. These massive beasts of power are virtually invisible, yet they dominate the cosmos in ways we're only beginning to understand. Imagine something so powerful it can trap light itself, a force so intense that anything caught in its grasp is lost forever. That's a black hole. One of the most intriguing aspects of black holes is their immense size. A single black hole can weigh 2 to 4 million times the mass of our Sun, and yet they remain invisible to us, hidden in the darkness of space. But thanks to decades of relentless research, we've gone from knowing absolutely nothing about black holes to gaining an up-close and personal understanding of these cosmic giants. And just when we thought things couldn't get any more mind-blowing, physicist Mikio Kaku announced something groundbreaking. We've finally gotten a glimpse of what lies inside a black hole. This new revelation sheds light on details the scientific world might have missed all along. Before we explore Mikio Kaku's discovery, let's rewind to the beginning of our journey with black holes. Back in 1916, Albert Einstein published his theory of general relativity, predicting the existence of black holes. At that time, the concept was purely theoretical. It wasn't until the 1960s that the scientific community found the first evidence proving black holes were real. The breakthrough came while studying the Cygnus constellation. Scientists noticed an unusually bright blue star emitting X-rays. This star wasn't just shining on its own, it was orbiting something massive and invisible. Upon further investigation, they discovered that the X-rays were being sucked into this mysterious object. This was our first encounter with a black hole, later named Cygnus X1, located about 6,000 light-years from Earth. And it wasn't just any discovery. Cygnus X1 is around 14 times brighter than our Sun and incredibly dense, with a gravitational pull so strong that even light cannot escape. The concept of a black hole is both fascinating and terrifying. It's a region of space where gravity is so powerful that anything, even light, gets trapped, never to be seen again. This danger only heightens our curiosity, making it even more crucial to understand everything we can about these cosmic monsters. Was Cygnus X1 the end of our discovery journey? Far from it. After this discovery, scientists embarked on a mission to find more black holes. What they found was astonishing. There could be over 100 million black holes in the Milky Way alone. Yet, because they are so incredibly difficult to detect, we still don't know the exact number. What's clear is that black holes are abundant, even in our own galaxy. The main issue with black holes is their gravity. Their gravitational pull is so intense that anything entering a black hole is compressed astronomically, eventually becoming a singularity, a point where the laws of physics as we know them cease to exist. In simpler terms, black holes are like cosmic vacuum cleaners, pulling everything into their event horizon. One of the scariest things we've learned about black holes is what would happen if a person were to fall into one. They would be stretched literally into a single line. This process, known as spaghettification, would occur gradually, and the person would perish long before reaching the singularity. It's a terrifying thought, but one that underscores the need for us to continue studying these enigmatic giants. So let's just say that no one should be stepping into one. But they're all over, so could we really be in danger? Despite the fact that the closest black hole to Earth is 1,500 light-years away, it's still close enough to bring up questions and concerns. In 2021, scientists were able to release the first clear photograph of a black hole, specifically the M87 black hole. This black hole was photographed several nights in a row, and with each photograph, the researchers gathered more and more evidence about it. They had to stitch the individual photos together to create something that filled all the gaps. This way, they were able to figure out that there are 3 layers to a black hole. It's not just one single gaping hole of nothingness, as many people believe. Things are a lot more complicated than that. To even get to the nothingness part of a black hole, you have to make it through the first 2 layers. The first layer is called the event horizon. While in the first layer, it's the point of no return. Once you pass the event horizon, there's no turning back and you will be sucked into the black hole. It only gets worse from there on out. The second layer is the photon sphere, which is the region where light orbits the black hole. Any light that enters this region will be trapped and will not be able to escape the black hole's gravitational pull. Finally, we come to the third layer, which is the singularity. This is where everything that enters the black hole gets compressed down astronomically until it becomes a singularity. The singularity is a point in space-time where the laws of physics as we know them break down, and we just can't predict what happens next. At the singularity, the density is infinite, and the laws of physics as we know them cease to exist. Now, what makes all of this infinitely worse is the fact that every single black hole you study will be entirely different from the last. Sure, they do tend to follow the same three-layer concept, but the way they function could be vastly different. If this were anything else, all we'd need to do is hop back on those telescopes and just study the problem at hand in detail. But with black holes, you can't really do that. Scientists can only study black holes indirectly by observing the radiation they emit and the gas and dust that surrounds them. Sending a probe, like the Voyager, inside a black hole is not possible because anything that enters the event horizon is pulled towards the singularity, where it is compressed to an infinitely small point. So, you can't exactly waste billions of dollars just to get a glimpse every time, because the second the probe gets close enough, it'll just be crushed into nothingness. Because of that glaring problem, scientists are left with no option but to study these objects in a two-dimensional way, even though they are three-dimensional phenomena in reality. To make matters even more challenging, there are also the two problems of every black hole being unique and the laws of physics as we know them breaking down when we try to explore the inside. This means that the traditional methods of scientific inquiry don't really apply to the study of black holes. That doesn't mean that the researchers haven't been busy. There are lots of different theories and explanations of black holes, and with each one, things get more and more interesting. One of the most compelling theories about the formation of black holes is that they are created from collapsed stars. When a star exhausts all of its fuel, it can no longer produce enough energy to counteract the force of gravity that is constantly pulling inward. As a result, the star begins to collapse in on itself, becoming smaller and denser as it does so. If the star is massive enough, this process can continue until it becomes a singularity. To understand the nature of black holes in depth, NASA scientists turned their attention to the core of the galaxy M87. Astronomers observed a super-powerful whirlpool of super-hot hydrogen gas that was spinning at an astonishing rate of 1.2 million mph. The sheer force of this spinning disk of gas should have caused it to violently fly apart in all directions, but it didn't. Scientists deduced that there had to be a colossal mass concentrated at the center of the galaxy to prevent this from happening. This massive object weighed as much as 2 to 3 billion suns and could only be a black hole. But that's not the only theory where black holes spin. In 1963, the New Zealand mathematician Roy Kerr used Einstein's equations of gravity to provide the best description of a spinning black hole. Kerr showed that a spinning black hole wouldn't collapse into a point as previously thought, but into a ring of fire or a thin disk. The disk would be spinning so rapidly that centrifugal forces would keep it from collapsing. This spinning disk of matter is called the ergosphere, and it is the region surrounding the black hole where the laws of physics start to break down. But the most intriguing feature of Kerr's solution was that it predicted the existence of an Einstein-Rosen bridge, also known as a wormhole. This is a theoretical passage through space-time that connects two separate regions of the universe, or even two parallel universes. The idea is that if one were to fall into a black hole, instead of being crushed to oblivion, one would be sucked down a tunnel through the ring of fire and shot out a white hole in a parallel universe. To understand how this works, we need to look at the concept of space-time. In Einstein's theory, space and time are not separate entities, but are interconnected, forming a four-dimensional fabric called space-time. Objects with mass warp this fabric, creating a gravitational field that causes other objects to move towards them. Now imagine a sheet of paper representing space-time. If you place 2 points on the paper and draw a line between them, this is a representation of how objects move through space-time. But what if you could fold the paper in half and create a shortcut between the 2 points? This is the basic idea behind a wormhole. It's a shortcut through space-time that connects two distant points in an instant. Wormholes aren't just a sci-fi concept, they are actually a prediction of general relativity, although no one has ever observed one directly. The reason is that wormholes are inherently unstable and would collapse almost immediately. But the existence of an Einstein-Rosen bridge would mean that black holes are not just cosmic vacuum cleaners.